Since it was installed in 2006, by the time we got there, it had exceeded its design life. 9 years is a long time for it to be standing open. We also required a deeper basement excavation, which necessitated some additional stressed anchors and passive soil nails below the existing lateral support to ensure that we can extend the excavation lower. Here are a couple of pictures of how we went about it. On the picture on the right, you can see we actually backfilled against and then put some pre-stressed anchors, post-tensioned anchors below the existing piles, and then we could excavate further down and reintroduce some gunite arches lower down. This is the typical section from one of the drawings that we produced to indicate how we go about it. The dotted line is the existing terrace level, and the solid orange line is where the terrace level would need to go. The geotechnical findings were that the allowable bearing pressure in the rock was 1 MPa and varies in depth from 1.5 to 5 meters below the existing excavation. So there are some fairly significant excavations that we had to do to get the foundations in. The existing mass concrete pad right in the middle, I'll show you a drawing a little bit later indicating the extent of it, but it was going to carry the lift core of the previous project. That thickness of the concrete pad varied between 2.3 and 6.3 meters with an allowed bearing capacity of 1.5 to 2 MPa. There's a 3 meter wide vertical dia-based dike which transverses east to west across the bottom side, from central south to east on the site. In terms of foundation solutions, piles are not really viable. The load is excessive, so the piles that we need to be in there would be either numerous or very big or both. And it's not deep enough really to get successful piling in there. So new pad foundations to bear on the rock head between the foundations or on top of existing ones where we could prove the competency of the existing ones were done. Municipal considerations that had to be undertaken were the laydown area in Ward Street, which was severely limited. We annexed one of the lanes in order to make sure that there was sufficient laydown area. The traffic impact of construction materials and the concrete delivery. There was diversion of some existing exposed services, particularly along Ward Street, and then connection of the new project stormwater and sewage and potable water to the municipal reticulation had to be quite in-depthly considered. During construction operations, we broke ground in the excavation on the 17th of November in 2015 after the lateral support system was re-engineered. We put in a new access ramp into the excavation and commenced demolition of some of the redundant concrete bases and columns. And we reshaped the basement to suit our needs. That's a picture of, in progress, demolishing the existing foundations and reshaping the excavation. Some of the challenges that were faced during construction, as I said earlier, some of the excavations were excessively deep. There's a groundwater issue. So you can see in the picture on the right, the guys are pretty deep and down in a hole there that had to all be filled with mass concrete before we could put the foundation pad on there. Every single excavation was checked by the geotechnical engineer and proved to carry at least the 1 MPa that we had prescribed. On logistical issues for construction, once the slabs are complete, they were often used as laydown areas, but it had to be moved around. So material was hoisted onto every 4th floor once the tower got going. If you can see, I'll show my mouse here, there's a little extending platform out of the building, and those used to dot the facade of the tower, and materials are lifted in there and then moved around inside for building the walls and all the internal stuff. 2 tower cranes were deployed on the site, which could access 95% of the structure, and the small areas where they couldn't access was done by mobile cranes. Man and material access was by sky climber lifts on the outside of the building. So concrete was supplied for 42-month construction period on a 24-hour-a-day basis to achieve a 7-day floor-to-floor cycle to ensure continuous uninterrupted supply of ready-mix concrete. There are backup facilities in place in case of any breakdowns, and continuous communication between the contractor and the ready-mix plant to ensure that the correct concrete mix specifications are delivered according to project time and plan. To keep traffic disruption to a minimum, the attempt was to make large pours after normal hours. Picture shown there is of the main foundation for the lift core. It varies between 2 meters thick on the outside to 4 meters thick on the inside, with some pits in there for dewatering the lifts. Now, conventionally, concrete is pumped up to a height of 50 meters quite successfully, but for this project, we need to pump to a height of 225 meters. To maintain pumpability and to avoid pipeline blockage and excessive heat generation and aggregate segregation, we had to use a hybrid plasticizer in conjunction with the super plasticizer. The concrete had a slump of about 180 mils, and the aggregate size, normally 22 millimeters for ordinary structural concrete, was reduced to 13.5 and 9.5 millimeters to counteract friction and to reduce the pumping pressure. Concrete strength grades in the same pour varied from 35 MPa to 70 MPa. So the columns were at very high strength concrete, particularly low down. So when you have a 70 MPa concrete column moving through a 35 MPa concrete floor, you have a change in strength. So when we were pouring the floors, we got them to put 70 MPa concrete over the columns that had stopped below to maintain strength of concrete. The concrete was left mixable, workable for about 5 hours. In terms of control and tolerance, vertical alignment of tall buildings is critically important, particularly as all of the lift companies specify just about a zero encroachment into the lift core, which is very difficult to achieve. So traditionally, laser beams guide construction of lift cores, but for tall buildings, inaccuracies occur due to wind gusts, crane impact, and other construction-related factors. To control the plumb of the Leonardo lift core, the state-of-the-art GPS technology was deployed. The system has a series of automated sensors to deliver precise coordinates and are not influenced by building movement. So they will survey the top corners of the lift core. As you can see on the right there, the picture is of the lift core projecting 3 floors ahead of the floor that we're busy constructing. They would survey the top, and after they poured the concrete, they would survey it again to see if it had moved at all. Coordinates are used to monitor the position of hydraulic climbing formwork and the slab edge prior to each concrete pour and after each concrete pour. One of the features are the keyhole columns. We'll talk a bit more about this a bit later. So they're 11 meters high. They meet strict architectural quality finish. So the cast is very important. External vibrators were mounted onto the shutters, and the concrete was pumped from the bottom up to start. And then once it got to a certain height, those holes were plugged and it was pumped from the top down. Each column carried about 19 tons of rebar and 55 cubic meters of concrete. At the very top, the viewing deck, the 56th floor, the feature cantilever slab canopy is an architectural feature topping the building. To support the slab, several fin walls rise above the building with steel hangers anchoring the slab to the fins. Those fin walls are continuous with the walls for the lift core, so they go all the way down to the bottom. So the formwork for the decorative coffered soffit was constructed to a height of 3 floors. You can see the portions there where the coffers are omitted. That is where the hangers attach. Alignment of the steel hangers was critical and very difficult to achieve. And the nighttime lighting on the hangers is a signature feature of the building. This is a view on the top. Those are the hangers down. The circular part at the top is just a cover to hide the cast-in bolts that were placed in there to tie it to the fin walls. Some of the construction elements, typically the basement parking are 230 millimeter post-tension slabs with unbonded 12 millimeter cables. Most of the superstructure is 425 coffer slabs with areas of 325 coffers when you need patios. We had to camber the floors to account for the deflection that would happen because of the large spans. The beam strips were 425 deep strips with post-tension cables. We used a bigger cable in those with the 260 MPa guts. The feature structures are the keyhole walls we mentioned, the cantilever viewing deck. The retail level, which is level 2, is hung off the parking level 4 because it is the front edge or the southern edge against Maud Street is set back to allow for a large volume entrance coming into the Leonardo from Maud Street. And then the various feature staircases inside of the building itself. There's a movement joint between the tower block and the podium and with the pool deck that is allowing for differential vertical movement as well as horizontal movement. Demising and partition walls were clay masonry walls in general, although higher up we used the autoclaved aerated concrete lightweight blocks to reduce load. I'll speak a bit more about that later. And in the hotel are drywalls and X-rated firewall partitions. Stormwater management, so runoff on the podium was collected in a previous siphonic roof drainage system, and then attenuation tanks to control discharge into the municipal system. For the facades, there were no external scaffolds. All of the cream-colored panels are decked on, which is a quartz, porcelain, and glass compound, often used for countertops, but very effective for waterproofing the outside of the building. There's glazing with variable opacities. The decorative laser-cut steel plates on the parking levels, as you can see in the picture on the left. You can see there's, I'll move my mouse again, up here is a little U-shaped stainless steel divider between the balconies, which extends all the way up to the spire on top of it. You can see from this side, the balconies at the bottom are bigger, they protrude more, and it gets less and less as you go up. On the other side of the Leonardo, the top sticks out more than the bottom, and it's a reverse curvature. These are two of the feature staircases. There's the spiral staircase in the restaurant on the right, and then the floating staircase with the artwork around it on the left, which is in the retail mall. A lot of South African local artists were employed to put their stamp on it. You can see a mural on the left there, and then that's the artwork inside that floating staircase on the right. Stormwater and landscaping. The podium paving forms a plenum to drain stormwater runoff from the facade and the pool deck into attenuation tanks. The landscaping is a feature on the rooftop gym and spa. And then the pool has an inner shell, which is contained by a structural concrete recess. So the structural concrete is not waterproof. There's a shell inside it, which all the waterproofing is applied to. Architectural features, there's a canopy cantilevering over Maud Street entrance on the right. And then the restaurant beneath the keyhole columns overlooking the pool deck and the local artwork that I mentioned previously. Some of the statistics, 42-month structural construction, 56,000 cubes of concrete, an average of 45 cubes a day, 9.5 million kilograms of rebar, 14,000 square meters of decked-on cladding and 28,000 square meters of glazing. The basement required 17,500 cubes of concrete, 1.38 million kilograms of rebar, and 40,000 square meters of formwork. There's about 2,000 direct jobs created on the site, as well as 20,000 indirect jobs. That's sort of an estimate of it. So in terms of design, some of the scope changes we had to deal with, we had to initially consider 3 scenarios. There's scheme 1, 2, and 3, where it was 34, 37, or 42 stories. The final scheme was 56 stories. On the left there, you can see it's a screenshot out of Autodesk robot analysis software showing the vector displacement under self-weight, under the 1.1 dead load plus live load. The color shows what the maximum displacement is as a vector. The red arrows are showing the service levels where there are outrigger walls. I'll speak a little bit more about that at the end. Which provide stability and activate the external columns and keep the building from slumping over one way or the other. So the scope change had an impact on the design, market-driven impact. The developer limited their risk by incrementally increasing the building house based on sales. So the more they sold, the more they added. The anticipated maximum height of the building was 50 stories. And so our initial column load takedown design and foundation design was based on 50 stories. But the actual building height in the end was 56 due to market demand. So the structural impact on that was that we had to increase the number of outrigger walls and service levels to 3 positions rather than 2. The column capacity had to be adjusted by you making use of the aerated autoclaved bricks rather than the clay masonry, which are about 60% lighter than the normal bricks. And then the higher it gets, the more influence the wind load has on it. So the floor-to-floor house was also reduced by the client, which added up to about a 3-meter reduction in the total height. Structural design and drawing production was impacted by architectural, HVAC, and wet services drawings revisions, particularly late information on slab penetrations for ducts and pipes. But you cope. Design considerations, the norm, we have to consider what the form of construction is going to be. So South Africa is typically we would construct out of reinforced and pre-stressed concrete, and very few buildings are structural steel systems in the country. So it's a function of architectural preferences, comparative costs, labor skills, market demand, fire performance, alternative load paths for progressive collapse, the dynamic response, and the technological expertise in South Africa, and developments in design codes. So it's interesting to note that prior to 1970, about 90% of the world's tallest buildings were made out of steel, whereas today, 85% of the tall buildings are constructed of concrete. You also have to take into account the behavior of tall buildings, or tall behavior. So the dynamic response of a tall building to load is very significantly influenced by the slenderness of the building and the natural frequency. So typically you'll have your fundamental load around the strong axis deflection, your second mode around the weak axis deflection, and your third mode will be torsional. And slender buildings have a much greater P delta effect, which is the secondary bending load effects caused by displacement of the center of mass. There's also had to be considered was the differential axis shortening of the columns relative to the central core under gravity loads. So the perimeter columns tend to be very highly stressed, so they will compress more, while the core, because it has a very big plan area, doesn't carry the same load per area, and so it doesn't want to shorten as much. So the perimeter columns are mobilized by outriggers and have been designed for compression and tension as a result of the overall structural cantilever flexure. Wind loads, the response of tall buildings to wind load effects directly impacts the serviceability of the building and comfort of occupants if the building motion is perceived. Wind load effects on dynamic and random in nature, in both time and space, and damping of excessive motion is required for slender buildings. Again, as we said, the slender building has a slenderness ratio of greater than 1:10, subject to steady long wind drag effects, plus fluctuating gusts and crosswind vortex shedding, and resonant wind loads affect the vortex shedding that are amplified when close to the period of the building. Whereas squat buildings, which is where the Leonardo lies, steady long wind drag plus fluctuating gusts, generally negligible for squat buildings in terms of resonant vortex shedding. Seismic action in South Africa, seismic less of an issue in South Africa in general, and slender buildings even less, whilst squat buildings a little bit more, but maybe as important. In our case, we did a seismic check. It was not as influential as the wind load. Now, sustainability is about adapting the use of a building while keeping the original structure. To future-proof a high-rise building, an important design consideration is a generous structural grid, column-free interior spaces, and appropriate live load allowances to ensure planning flexibility for future reuse. So you can have retail or office or residential just by adding additional partition walls inside, and you can reuse it. The challenges that we face, now this is really what the design side comes on. So because we had existing foundations that we had to try and deal with, you can see that, and some of them were pretty massive. The existing massive foundations for a previous scheme were interfering with our column layout, and the building design was to some extent impacted by the existing foundations, too large to be demolished. So in red there you can see we had new footings on top of existing footings, and the gray one was existing footings. Now, there's not much space left there for other footings, but as you can see, if I show my mouse, you can see dotted lines there indicating what the existing foundations are. We obviously try to fit in between those. I mentioned previously, I'd talk about it, but that area is where the previous scheme's lift core was going to go. It was going to be orientated north-south. Ours is orientated east-west. So our core sits half on the existing mass concrete, and then we had to make a giant excavation and pour more mass concrete in there, stitch it together, and then our foundation sits over the top of that. So the basement excavation lateral earth support. In this little picture on the right here, you can see that's the perimeter of the slab, and at every single pile position, lateral earth pile position, we have a little projection to support the lateral earth support. So the lateral earth support now is redundant, and the slab itself and the building itself is carrying the lateral load. Basement ventilation was facilitated by the voids between the piles and the slab edge. So where this little arrow is, it's showing a void in there, and that's how ventilation on both the north and the south side is dealt with in the basement areas. The lift core tolerance was quite a challenge. It's not concentric in the footprint of the tower block, which means that the floor slab on the north side of the tower block spans further than on the south side, which tends to want to pull it to the north. And because you've got staircases on one side and lifts on the other, it also wants to twist. So the building itself will lean to the north and then twist in an anti-clockwise direction. We designed it so that the total displacement was h over 1,000. So 250 mils roughly is the maximum displacement that any point on the tower block would be. So accurate GPS monitoring of the lift core alignment was necessary to ensure no encroachment of the structure into the lift shaft. In some areas it was not possible and some remedial work had to be done. The keyhole walls, so 44 stories of the north facade come down where that red arrow is there. That's about 40,000 kilonewtons coming down on top of that keyhole wall, and then it has to be distributed through a triangle onto the columns below. So you can see this double-headed arrow at the bottom here is a massive tension force that is generated in that portion of the structure. We have about, I think, 36 post-tension cables in there to tie those together to prevent it from splitting apart. So the feature provides about a 12 to 15 meter column free space in the central core, accommodating the different spatial requirements of offices, residential, accommodation, and hotel. It enhances the sustainability of the building. You can see that is now close to 12, 13 meters. That's the core wall, that's the facade column, and there's your the feature wall that we're looking at. Slab features, so to improve the serviceability and to mitigate creep deflection of long span columns, long span column free post tension slabs, the mid span pre-camber was about 40 millimeters. So we allowed for 40 millimeters total deflection before it was flat. Facade anchor plates were required to be accurately positioned to attach the facade. And then accurate positioning of the slab penetrations was critical, but I'm sure as many of you know, they never stay. So the outrigger walls was an interesting one. To start off with, the original intention was to have outrigger walls on one side only. So we can see here on the left, that was the original intention, at every single service level, we have one outrigger wall. Then unfortunate impact of that is that because the columns are heavily stressed and they wanted to shorten more than the core, the entire building would be pulled over by 1.5 meters to accommodate that, which is why we introduced a reciprocal on the other side to hold it back. So it then is much stiffer. Your lever arm between your compression and your tension faces becomes much bigger, and it's a far more stable structure. They're incorporated at each of the service zones, approximately 11-story intervals. They're also designed to increase the building stiffness, as I said, and we limited the deflection at the top of the building to h over 1,000. The maximum allowable is about h over 400, which is fairly significant. The other thing we did was we designed these outrigger walls so that if a column is broken just above it or just below it, the next outrigger wall can carry 10 floors worth of floors without collapse. There'll be deflection, but it won't collapse. In the viewing deck, the post-tension slabs and the hanger design was quite involved. The main issue with this was trying to get the holding down bolts in those fin walls in the right place so that it's at the correct angle to fit here. A lot of pain and suffering to get that right, but we did. The construction sequence was also critical. So we cambered the toes of the slab, or the outside. As you can see, it slopes upwards. We had to cast the bracket into the floor and cast the bracket into the walls, and then fit a set of steel hangers to that. One of the guys from our office spent a lot of time up there measuring and making sure that it fits right. This is the team that worked in it. It was a jolly fun project to work on. I'd like to acknowledge then the Legacy Group for being the developer. The financiers was Nedbank, Legacy Development Management. The main contractor being Avenge, architects, Co-arc, ourselves as a structural engineer, quantity surveyor SM Schneid, facade engineer Arabs, the MEP engineers Watzel, M&S, Wingrove, geotechnical was Joseph Wagner, interior design was Varoom, Falk, Stephen, interior design consultancy, landscapes by Landmark Studios, and the fire consultants were SFT, Specialist Fire Technologies. That's just a picture of Africa's richest precinct. So since the early 1990s, the Legacy Group has developed several notable mixed-use buildings within Africa's richest square kilometre. So each of the below buildings have been engineered by RMC in collaboration with a team of architects, quantity surveyors, MEP and related services. Nelson Mandela Square, before we were Ritchie Midgley, we were Leach Price, and we did that one. Michelangelo Hotel, also under the same banner. Then the Michelangelo Towers, the Da Vinci Hotel, Raphael Apartments, and later the Leonardo, which is where the picture was taken from. And just a little video to end things off. And I'd like to take the opportunity to say thanks again for giving me the opportunity to speak about this exciting project. Just before I move on, I'd have to say that one of the most standout features of this project for us as a company was the interaction with the contractor. The relationship between Avenge and ourselves was such that hardly any delay claims due to our work or their work. If there was a problem from their side or from our side, it was just a phone call, and everyone was very, very keen to assist to get the project to work. It was a standout feature of the building for myself. Makes everything much easier. Thank you.
Thank you very much, James. That was a absolutely interesting presentation, and I have many questions that I've written down. I'm just gonna, okay, we can actually leave your presentation in slide on, and we can go on with the questions and answers. So I'm gonna jump straight into the first question. Someone asked, what was the electrical challenges encountered?
Sorry, the electrical?
Yes.
Well, we weren't really involved in the electrical side of things. We're just the civil and structural engineers. So I don't think I'll be able to give much input on that, I'm afraid.
Okay. The second question, has any renewable energy solutions been implemented in this project?
Not so much. It was looked at. I wasn't involved in all of the discussions and decisions on it, but ultimately the use, because there's such a small surface area, so it's a big building for a very small area, so you don't get much exposure to the elements. So solar was not really considered. You don't get much space to put the solar panels on.
Okay. Okay, and then the next question, was there an energy management strategy implemented?
There was, but again, I wasn't really involved in that side of things, so I can't give too much feedback on that one.
Were there any international services used on this project, consulting or materials?
Sorry, international?
International services used, so either consulting or materials.
Well, so the Decton plates, I think, was imported. The Decton panels for the facade, but everything else was local. The engineering was local, the design was local, and the materials were local.
Okay. Someone's asking, Toby is asking, what software did you use for structural design?
Okay, so for structural design, we used a variety of tools. You don't sort of want to rely on one, put all your eggs in one basket. So wind load being very critical, we used robot for the CFD function, which is subsequently separated. So there's computational fluid dynamics, which is a computer-aided design for estimating wind pressures. We also used the Eurocode, a spreadsheet for Eurocode and SANS wind loading. We also had our own in-house developed spreadsheets that we used. But the majority of the design was done in Autodesk Robot Structural Analysis Professional.
Thank you. I've written all the questions down, so I'm just going through them. Let me go to the chat function. Derek is asking, who were the OHS agents and were any incidents noted?
Oh, I'm trying to remember what their names are. I can't remember off the top of my head. But I mean, there were a couple of minor ones, nothing major.
Okay.
You know, I think every site has small ones, but there were no major incidents that were a problem. And a couple of near misses and a couple of small injuries, but yeah, nothing major.
I see that someone's also posted, Chike posted in the comments, how did you navigate OHS related issues?
Yeah, more a contractor's responsibility. So the health and safety agent was appointed, and they were always on site. People walking around with their safety jackets on, looking to make the place safer.
Okay. Then, if you could just give us a brief explanation about what your engineering journey has been like.
Me personally?
Yes.
Well, I guess I graduated at the end of 2001. I ended up moving to Australia for 4 months and had to come back. I had met someone and is now my wife, so couldn't stay there. When I came back, I started working for ESAW before they were ESAW Frankie. And I was involved in I was a site agent for the lateral support and bulk earthworks for the Michelangelo Towers, which is how I met Tony Ritchie, who's the R in RMC, the Ritchie. And working on site, requested if I could work for them rather than work on site. And I've been with them since then. And it's been a very, the learning process has been rapid and never ending. So we're quite diverse. So we've worked in commercial side, we've worked in the mining side. I think buildings like the Michelangelo Towers and the Leonardo don't come up very often. I've been very fortunate to be involved in both of them. And I have to say that I feel gratified by my work. It feels like a noble profession. You're there to make stuff work.
That we are. Another question. I love that everybody's asking questions. It makes it so much easier. But obviously the talk was super interesting. Another question from Toby. You mentioned that the project was 50 floors, but later increased to 56. At what stage did you make the increase to 56 floors?
So the answer is after the foundations were cast, which is one of the reasons why we had to move on to the aerated brick construction. So the amount of brickwork internally to fit out the apartments and the penthouse apartments is significant. You think the weight of concrete is about 24 kilonewtons a cube, and the weight of a brick is about 22 kilonewtons a cube, whereas the weight of the autoclave is about 5, I think. So you save a massive amount of weight by replacing the masonry with the autoclave aerated bricks. You throw it in the swimming pool and it floats.
Okay.
So that allowed us to get those extra 6 floors into the building without having to change any of the major design or do any retro engineering. We looked at various options. You've got your hollow block construction. We looked at that. We looked at clay bricks with voids inside. But yeah, the from Hebel, the aerated bricks were by far the best solution.
Okay. We have another question in the comments. Was the lateral stability of the building relied on only the core wall, or was there any other schemes used?
So the core is the majority of it. So even though the outrigger walls attached to the outside columns, it still all comes back to the core. So we designed them in isolation as well as together. I can quickly go, if you don't mind, I'll quickly go back to the, no, sorry, I'm on the wrong, we'll go back to the picture of the, we'll get there. Oh, too far now, too many buttons. Am I still going backwards? Yeah, the interesting thing is we started working it in 2013. So we've done an entire design on it before they'd even broken ground, but the scheme changed several times. So just to go back, it reminded me, that picture is not what the building looks like now. You can see the entire top of it is different. There's only one floor. So this is the level that we had gone to by 2013 before that even started, and then we only started building it in 2015. So back to this one. So you can see this is for the self-weight deflection, self-weight and live load. We don't take the full live load because you say not every floor is going to be fully live loaded at the same time. So you have a reduction factor depending on the height. But this is showing that this corner is moved the furthest. So it's wanting to lean over and twist, as I said. So it all works together, but the core is where all of the stress goes to for the thing. So the secondary design is where we remove a column and see that everything else still works, and those outrigger walls can still carry the 10 floors either above or below, and make sure that it still stands. So yeah, lateral stability, it's a combination, but majority of it is in the core.
Darren Pillay is asking, what were the design fees obtained?
Never enough.
Never enough. Oh, okay. And then someone's asking if you could just repeat the software that you used in the design.
Okay, so we used Robot. This is an extract. This picture of the building is a screenshot out of Robot. It's an Autodesk product. We used the Captain module, which is the post-tension design module from Procon. We used that quite extensively. And then TEDS. For a lot of the hand calcs, we used the TEDS suite of spreadsheets and those design calcs.
What was the floor scheme used and what guided the choice?
So the floors in the podium, not in the podium, the floors in the tower block were all coffer slabs. So the benefit of coffer slab is that you get good depth. So your deflection control is good for less concrete. So you've got the voids, you know where your steel is, and it's quite versatile because you've got the ability to put penetrations through the coffer heads at a later date if you need to. So that's more what guided it than anything else.
Okay, then we have a question from Anonymous. Can you please explain the design considerations from the viewing deck on the highest floor a bit more?
Okay, if I understand the question correctly, let me go to, we've got some pictures of it. So effectively, what the architect was wanting was a floor that floats. So in order to get that, you can't have anything, we don't have anything underneath, so we put these hangers at the top. So these are two back-to-back channels, which are tied together with tubular sections. Cast into the concrete here is this bracket. Those bolts are installed afterwards. So this whole, oh, damn it, go back there, click the button accidentally. This whole bracket is cast into the floor. There are post-tension cables which lift it up, and then these channels, they bolt on here, and they are tied at the top here to a cast-in plate into the fin wall. So they're just in tension. And then the last little bit of the floor is, you can see that's where the bracket is cast in. and that little bit just cantilevers. This was quite the difficulty of it, not so much from a design side, but from an aesthetic side, is that it's all exposed, and your most expensive apartment is just underneath there. So the off shutter finish had to be quite strictly done. So all of these edges, you can't quite see it, but it's rounded. Those shutters were all purpose made just for this floor. So yeah, it's just basically intention. Go back there. So these hangers are intention, tying the wings back to the core walls, which are extended. I hope that answers the question.
What were the major challenges? Could the project have been finished in a quicker time than it was?
I don't know how to answer. The major challenges, so they vary. To start off with, the major challenge was to try and fit it inside the existing foundations without being too influenced by what is already there. The next major challenge was the fact that founding was 5 meters down in many of the cases. Groundwater was a problem. But once construction got going, no, not so much. I think that the main limitation was that it was only very late that we got finality on what the final height was going to be. It was, at first it was only 37, then it was going to be 42, then now it was only 40, and then it was, okay, that's 50, oh no, it's 56. So that sort of, you don't quite know where you're sitting, was a difficulty. We had to discuss and agree that we had to do multiple designs to make sure that regardless of what the final scheme is, we had the service levels with the outrigger walls fixed. So we had to try and get that buttoned down quite early, so it doesn't change. So at the moment finally it's got 3, but there were options for it to have 2 with being a lower building. But we can't, it would be very difficult to carry more than the 10 floors above it if a column was knocked out.
Okay.
I'm not so sure if it could be done quicker. Maybe. The structure itself. So the finishes, I think, take a bit longer though.
So we have a question asking, with your experience, what could you have done better on the project?
It's hard to say. I think overall the project worked very well. The relationship with, as I said, the relationship with the contractor was very good, but the relationship with the architect was good, and all the other professionals. It was a very, overall during construction, it was a very happy project to be on. There's obviously pressure, and at times it sort of spills over, but our team's relationship with the guys on site, that relationship was just outstanding. In the 20 years that I've been working, I have not experienced that on any other project, where there's just this willingness to make sure that the project goes ahead. If there's a problem that we've made a mistake, call them up and say, can we sort this out? And they say, no problem. And if conversely they have a problem, they say, oh, damn, we've got this problem. Can you come out and help us? And we'll pop in the car, drive there and say, this is how we need to fix it on site. So it's a very active role of doing that, as opposed to some of the other projects where, you get a letter with a technical query, and then you have to spend your time answering it. It adds sort of 2 or 3 days each time to try and respond to that, rather than just saying, I've got a problem, come and help me, and off you go. Also helps that the project is in Sandton, so it's not miles away. If you have to drive out to, say, Rustenburg, it's not quite as easy to do that type of arrangement.
Okay. Then we have another question. We actually have 2 more questions and then just one from my side. Did you consider story drift effects in the design considerations, considering the height of the structure, and how did you go about it?
Yes, so we did consider the story drift, or the P delta effect. So you do a second order nonlinear analysis, and you check that it works. So it's all functionality in robot.
Okay. Then the last question from the chat function. Was the building on piled foundations? If no, what type of foundation was considered and what guided the choice considering your ground water effects?
Okay, so no, it's not on piles. Part of the limitation is that the load is so big. At the bottom, your heaviest loaded pile is about 60,000 kilonewtons. To try and carry that on a piles or on a pile with a pile cap, your pile cap is going to be about the size of your pad foundation anyway. So that's the one reason. The other reason is that your bearing capacity or your founding level was between 1.5 and 5, maybe 6 meters down below the terrace level. You can't really get an effective pile in that depth. So we didn't look at piling. It was briefly considered, but dismissed for those reasons.
Okay. Thank you, James. I know that was a lot of questioning.
No problem. I'm happy to answer questions.
I think everybody thoroughly enjoyed your presentation and it was really interesting. Your last comment from my side, what message would you give young professionals as an individual or as an expert engineer?
I think the message is that your learning is never done. I think I'm still learning new things on new projects now. You never, our principal, Mr. Don Midgley, he's reaching a riper old age now. Let's be careful, but he's still learning stuff. It never ends. And I find my experience has been that it's very diverse. You seldom are stuck in doing the same thing day in and day out. You have the opportunity to go to site, which is nice, but you've got the opportunity to sit in the office, which is nice. You've got the opportunity to do design work, which is nice. You've got the opportunity to do measuring or estimating, which is also nice. You can do steel design, you can do concrete design. If you don't like that, you can go into contracting. It's a very, very wide field to be into. So I think I guess the message is there's room for you.
Okay. Thank you so much, James. We really appreciate it. And thank you for taking the time to come and chat with us.
It's an absolute pleasure. Thank you very much.
Thanks. I'm just going to share my presentation one last time. So this was basically our question and answer slide, and just the picture on the left-hand side shows us civil engineering versus architecture. And on that note, I would just like to thank our annual sponsors, because without your sponsorship, we would not have the ability to do what we do. And I'd like to thank everybody for joining us on the webinar. I think that it was absolutely amazing, and James's presentation was so informative. And a final bit of exciting news: the CESA on Engineering Excellence Award submissions are open. So please visit the CESA website for more information and to submit your projects. And then just in closing, engineering has been changing the world for millennia, and the new rapidly emerging technologies are an opportunity for positive transformation that leaves no one behind. Thank you guys for joining, and I hope you have an awesome day.